All right, welcome everyone. Thank you for being here. First day of SIGGRAPH, and this is a proud tradition of Khronos Fast Forward. So in the tradition of Fast Forwards, we have way too much information and not enough time, so we're just going to dive straight in. My name is Trevett, so my day job's at NVIDIA. I'm the Khronos president, and happy to be here with a bunch of speakers who will introduce themselves as we go. The purpose of this 1 hour is to give you the headlines of what Khronos is doing, if this is your one contact with Khronos here at SIGGRAPH this year, and hopefully maybe even to inspire you to come to some of the BOFs that we have during the week. There's a lot of content from Khronos if you're interested in more details. So if you haven't come across Khronos before, we are an open standards consortium. We're open for any organization to join. We have around 200 members, we're global. We do open royalty-free standards, mainly APIs for software calling into hardware, like GPUs, but also asset formats. Our standards are free and open for the industry to use. We love SIGGRAPH, of course, because we do a lot of 3D, but actually all of the standards we do have a lot to do with spatial computing. We're not going to go through all of these today, but we have a camera API that's in development for the front-end sensor handling. We have lots of compute APIs, inferencing, vision, and image processing. We have OpenXR for portable augmented virtual reality, and of course the family of 3D APIs and the glTF 3D asset format to feed those APIs with 3D content. So this is the chart of the currently active standards that we have, and the red box is where roughly we're going to be focusing in today. Before we dive into the first, we're going to cover OpenXR first. Before we do that, just want to mention a potential new working group. We have a new initiative process at Khronos. Anyone can propose a new working group or a new initiative, and NVIDIA has just proposed one. It's a Slang shading language. It's in the exploratory phase, so we haven't decided if and when or what we would do, but this is the proposal, and I think it may be of interest to folks here, so we mention it, because if you're interested, of course you can join the Khronos Group and get involved in the discussion. So Slang is a shading language. It's been in open source for many years. It comes out of research at NVIDIA. Slang is a forward-looking shading language, a language, domain-specific language for shaders to really enable shader programmers to do much larger code bases that are maintainable, reducing your compile times, just good software engineering for shader writers, and looking forward into machine learning and neural shaders too. The Slang open source compiler also ingests GLSL and HLSL. So if you have existing code bases and you're interested to try out the Slang compiler, you can take your existing code and bring it in. And it has lots of backends. I won't read them out, they're on the screen here, which maybe means you can have your shader code written once and you can deploy it on all of the platforms that you care about. So again, this is just an exploratory phase, but we do have a BOF session on this as part of the Vulkan BOF, which is on 3 p.m. on Wednesday. So I'm going to cover OpenXR, and then I'm going to hand off to my colleagues here. So OpenXR is solving the classic portability problem that augmented and virtual reality faced. Every hardware vendor had a proprietary API, which is a real pain for the software developers, have to keep rewriting. OpenXR provides an API into XR runtimes, and so software developers can write once and deploy anywhere, creating the possibility for cross-platform, portable, immersive experiences. The great news, because no standard is worth anything if it's not widely adopted, is OpenXR is truly widely adopted. It's actually hard to find any XR hardware now that doesn't support OpenXR. all of these on the screen, again I won't read them out, they're all conformant to the OpenXR API, and it's not just headsets, it's some of the stereo displays as well. We just had a pretty big release, OpenXR 1.1 release in April, and it really marks a shift in how the working group is going to be working going forward. From the release of 1.0 up to 1.1, it set a baseline. 1.0 set a baseline, but there was a lot of experimentation with vendor extensions on potential new use cases and functionality, which is great because OpenXR, like any Khronos API, is extensible just for that reason. But at some point you have to consolidate, because if you let everyone go off and do their own thing, of course you get fragmentation. So 1.1 starts that process. We've consolidated some of the vendor extensions into the core spec, and it marks the phase of this new way of working where we recognize that we need to do that to prevent fragmentation in the industry. But at the same time, we're also looking at new cases too. So we've got to hopefully keep the balance correct between the two. The things that were promoted into 1.1, there are things like local floor reference spaces, so an estimated height is built in, so you can calibrate very easily, better orientation to the user's hands and hand devices. Optionally, OpenXR 1.1 supplies foveated rendering for XR headsets. There's more in there. All the engine vendors also have OpenXR backends. Again, I won't read them all out, but Unity and Unreal and many others, and the WebXR engine, its default backend is OpenXR, because OpenXR enables WebXR to avoid having to write to dozens of pieces of hardware. And this is another good example. We love working alongside the W3C. We have WebGL using the native APIs, we have WebGPU using the native APIs, and WebXR using the Khronos native APIs. So this is a good pattern going forward. So things that are coming to OpenXR, we have pretty extensive hand tracking in 1.0 and 1.1. That's going to be extended out, both the hand tracking itself and extending out to full body tracking. I think the big thing is spatial entities, where OpenXR is going to move beyond just controlling the device, but providing an API to scanning and understanding and handling and interacting with the user's environment. So that's what the working group means by spatial entities, standardized ways of doing that. And we're finding that there's quite strong consensus in the working group members at OpenXR to find a common way to do that. So things are looking hopeful that we're going to find a good solid way to really make OpenXR a spatial computing API. Expanded haptics, and we're even going to use glTF. We'll talk more about glTF later, but one of the things coming is you'll be able to model and display your controllers and devices actually in glTF models as part of the standard. So, fast forward, that's what you're going to get for now. Slang in, this is the wrong box. There is an OpenXR box. I'll find out the time and I'll create that before we get to the end of the, it's on Wednesday in the morning, and I'll find out the time before we break. So, that's me, Tom.
You're on the clock.
Yeah, we're ahead of time.
Yes, I know. How did you do that? Hello everyone, welcome. My name is Tom Olson. I work for ARM, and I'm chair of the OpenGLES, was once chair of the OpenGLES working group, and now it's development. And I advance slides how. Right. I will say, so for my segment, this being SIGGRAPH, I'm not going to explain what Vulkan is, assume you know. Wednesday at 3 p.m. to 6 p.m. we have a 3-hour BOF in which I and many other people, 5 other people, will tell you kind of what's going on in the Vulkan universe today from various perspectives. So that's 3 hours. I'm going to present the same material in 6.5 minutes. So it's going to be, well, if you keep track, that's 26:1 compression, lossy. This is kind of a big year. It's a milestone year for Vulkan. This didn't hit me until January when I looked at the calendar and realized it was 10 years ago at SIGGRAPH that we announced the plan to develop a new kind of API that would address problems people were finding with OpenGL. And that led to Vulkan 1.0 18 months later, and was the start of the journey that we are still on today. Oops, sorry, I forgot to show you the cool picture. That was me when I had brown hair, but it was dyed then too. So at the BOF, this is how it's going to work. I have I'm the lead off hitter, and I'm going to start by looking back at some of that ancient history and talk about how Vulkan has evolved and some of the lessons we've learned along the way. I will also talk about how we're trying to manage Vulkan's evolution going forward in a more systematic way. We don't want it to grow sort of free-for-all. We want it to be planned. After that, I'll talk about what is new in the API, technically speaking. The biggest thing we've released this past 12 months is the Roadmap 2024 profile. If you hadn't heard, I'll say it one more time, roadmap profiles are the new hotness. Don't think about core versions. Roadmap profiles are they play the role that core versions used to play in terms of signaling. This is what you can expect to find in reasonably close to state-of-the-art hardware, including mobile hardware, in this particular time frame. So this profile is aimed at end of 2024. This is what we expect to be hitting the market and becoming the new standard in that time frame. At the BOF, I'll go over the technical content. It adds quite a bit of things to the previous roadmap profile, but I don't have time for that now. Also at the BOF, I'm going to talk about the future. This is something we have historically not done, but as part of trying to guide the evolution of Vulkan in a more systematic way, we're going to start exposing more of that. So the goal here, we have these technology buckets that go out to 2028, and we're starting to assign things to 2030 a little bit. And the goal is to make sure that when we arrive at a point when there's a technology that developers need and that GPU vendors can provide, we have an API for it ready to go. We don't want to be the blocker that's holding back progress. So after that, after I've talked about the future, I'm going to switch to talking about what's happening in the ecosystem. I won't talk about the SDK because immediately after I speak, Karen Gavam, CEO of LunarG, will talk about the evolution of the SDK. When she's done, Jeremy Kevin, who works for her, will talk about a cool new tool in the SDK. It's only 2 weeks old, I believe, which helps you find out what went wrong if you get a device lost error or the GPU just wedges and you have to hard reset it. Those are terrible things to debug. We now have some tools which we hope will help. Shading languages. I was actually going to talk about this in the things we're working on section, not the ecosystem section, but I wanted to tell you about it. So let me go into this. Not the most cheerful story, but I'll do my best. Vulkan has a kind of complex relationship with high-level languages. In theory, it's completely high-level shading language independent. Everything's defined in terms of SPIR-V, and in theory, we don't care how you generate that. But in practice, that's not good for the ecosystem. We need some consistency, we need some standards. So we do worry about this, and we try to make sure that your shading language needs are met without locking you down. It's a balancing act. I don't think we're balancing terribly well at this point, but we're working on it and trying to get better. The first thing I want to say, if you love GLSL, don't worry. It's not going away. It's going to be here forever. It has a niche, and it's useful and essential, but it's kind of the C99 of shading languages. It's, you know, if you're doing, it's fine for certain tasks and it's even great for certain tasks. But if you're trying to do large-scale software engineering, it's maybe not that well suited. You might want to think about using something else. For some of our developers, something else automatically means HLSL. That's the only thing they will consider. We get that. We're doing our best to support them. I do want to give a shout out to Microsoft. The HLSL team there has been great about being welcoming and supportive of our efforts to make sure that you can generate Vulkan-ready SPIR-V through the DXC compiler. But of course, they can't do that work for us, and it's expensive work. We don't have a good funding model for it. It's kind of, we're not quite sure how that's going to work out. And then there's the Slang option, which just emerged in the last 6 months, which Neil talked about earlier. We're very interested in this and excited about it. We don't want it to foreclose HLSL or GLSL, but we think it's really interesting and very cool. So at the BOF, again, Hai Nguyen, my good Khronos buddy of longstanding, will talk about using Slang with Vulkan. Turning to use cases and applications, took 4 or 5 years, but Vulkan Video has driven the golden spike. They now have an end-to-end complete chain that will take you from a compressed bit stream to pixel photons hitting your eyeballs in Vulkan, which is really cool. So Vulkan Video is now officially supported in mainline FFmpeg 7.0. It's supported in a stable release of GStreamer, and therefore anything, for example, the MPV player that makes use of it will pick it up automatically. If your hardware supports that device, you may have to do a setting or something to tell it to use Vulkan. But it's already there, and as I say, it's in mainline releases. It's not experimental. Further work ongoing to support AV1 and to support encode, but that's not actually, AV1 decode has landed in FFmpeg, but more decode work to be done. I did want to mention that ray tracing is finally reaching mobile. It's kind of old hat on the desktop, but there is now hardware support from ARM and from Qualcomm in mobile SoCs. And I've seen some really cool content. My friends at Samsung let me see some ray traced mobile game content that is coming that is pretty awesome. On that note, in the BOF, Jasper and Darius from Traverse Research will talk about a benchmark they're building that will give those ray tracers some serious work to do. Last thing I'll talk about, the growth of professional rendering in Vulkan is particularly dear to my heart. It's been going on for a long time. Both Adobe and Autodesk started using it 4 or 5 years ago with Premiere Rush and Substance Stager and Fusion 360 from Autodesk. Autodesk has done amazing work since. They've kind of they're Vulkanizing all the things. And so they're making all kinds of interesting uses in various contexts. And therefore, the grand finale, what am I showing you? Wrong slide. The grand finale of our BOF on Wednesday, Henrik and Ashwin from Autodesk and Caroline from Pixar will talk about how they are leveraging Vulkan in the OpenUSD ecosystem by integrating it into the HydroStorm renderer. And that will be a great talk, and I'm really looking forward to it. There's other ecosystem news, but I'm concerned that I'm out of time, so I will stop there. Thank you. How did I do?
Awesome. Yeah, thank you, Tom. And coming up, Jeff. I forgot to mention that we will have time for Q&A at the end, so get those questions ready. And there are some empty seats down here if folks want to come on down. Come on down. Jeff, over to you.
Hi, my name is Jeff Amstutz, and I get to work on ANARI, which is a really great, fun standard that's went 1.0 last year. If you are asking the question, what does ANARI mean? It doesn't actually mean anything. Turns out naming is really hard. Unfortunately, what ANARI is can loosely be defined as the Anonymous Application Rendering Interface. That's not the history of why we picked that name, but I would love if we could land on that. So the problem that ANARI solves is this one, it's like a software engineering problem where if you wanted to be an application developer to say, I want to use a particular rendering engine, you have a software engineering effort, so you have to integrate with that engine. And so you get this mess of applications having to talk to end 3D rendering engines. Everybody has to do the same thing over and over again. And this ends up being really, really inefficient. And that's just 3 applications and 4 engines, and it looks like a mess. So what ANARI strives to do is say, can we get applications able to use these rendering engines with an API that looks the same, that you spell the same way? And for rendering engine developers to say, could all of my applications above me look the same? That doesn't necessarily mean the features are the same, the things that are important to those applications for what gets used, but rather just the API itself, how you spell it, would end up looking the same. Now, a tricky part of defining any portable API standard is balancing what does it look like to have uniformity you can depend on in an API, and then have feature differentiation for how do implementations bring their unique value to applications. And these 2 lists are fundamentally where that tension is. Can you get objects to look the same? How do you set parameters on them? How do you express array data, and how do you, and the ownership of those? Concurrency and parallelism, all the things that go into designing an API. We really believe that when you interface an application with an entire rendering engine, that these are the things that don't need to change. We don't need to spell them differently. And then there's all kinds of ways that engines can differentiate. So we're not trying to all implement the same renderer. We're trying to say everyone can have their things that they want to differentiate on. It could be just what features you decide to go after at all, the different dimensions of performance that you find important, particular hardware you want to support. Of course, image quality. Everyone wants to make the prettiest pixels possible. And then one that goes unsaid in some places is scene size. Not everyone has ridiculously sized scenes they're trying to render, but there are plenty of people that do. And there's different ways you can solve that. And each one of those are good implementation details. What we're trying to do is say, let's not pick one and say everyone has to do just that. And the way we do this is ANARI strives to say applications express what needs to be rendered and when it needs to be rendered, but not how it's to be rendered. And I think the balance of that would make more sense in the software stack for how this kind of all shows up together in one application. So at the bottom of the stack is pretty obvious. You're going to eventually be running on hardware. It's generally GPUs and CPUs and other things. And then right above that, to program those devices, you are going to look at graphics and compute APIs. A lot of the things that Khronos standardizes, there's other options too in the industry. And the important thing is that's exactly where you say how something gets rendered. You need to figure out how buffers get to the GPU. How do you make shader pipelines that can actually make pixels of the content that you've been handed. And then when you build an engine, that's the thing that ANARI actually talks to. So those are a number of offerings. I really hope that list explodes to be as many engines as there are in existence, but the place that ANARI sits is above what an actual engine is, and keeping applications out of the how. And then of course, I put this little box scene graphs in 3D applications, because of course you have to describe your scene with ANARI. But generally, scene graphs that are trying to solve particular problems, rendering is only one of them. And so ANARI is not trying to say we have to solve every problem for you would represent in 3D, but rather you just barely share that with ANARI for what your scene was that you were doing all your other operations with. And then eventually when it hits a renderer, that's what ANARI is expressing. And so just a real whirlwind tour of the history of ANARI and how we got to this point. We started as a working group in 2020, and that was a great time to start working together. Had a lot of virtual work, and it's great that that's how we operated anyway. And then in November 2021, our first provisional spec came out, and you can see in the bottom track we did lots of iteration on the spec itself, as looking at PBR materials, some interface tweaks based on experience, and that came from the upper track. Ever since we started the provisional spec, we've been all about having an SDK that you can use right away. And so we co-iterated those things together to bring us to August of last year. So unlike Vulkan turning 10, we just turned 1. And so August last year, we released ANARI 1.0, and that's really what 1.0 means is we've started the foundation of the things we think we don't need to change anymore, won't change. And now it's about adding things that we all agree on as we agree on them in practice. And then we just released an adopters program to help us secure the future, like our conformance test suite and stuff. Had some SDK releases, and we're working on 1.1 already in the spec. One thing I wanted to highlight very briefly is if you Google this paper, Standardized Data Parallel Rendering Using ANARI, some really exciting work. It's freely available if you want to read that paper. It tells the story of how we had some data parallel path tracing, so multiple computers filled with GPUs, being able to path trace the scene spread out on all those computers. And being able to do that with ANARI without having to prescribe any of the implementation detail to balance that with traditional sort path compositing. I think it was a great piece of work. I really highly recommend you checking that out because it's really, really innovative, and ANARI was a key piece of bringing that to real applications. And so at the BOF, which is going to be on Wednesday at 10 a.m., I believe, there's a lot of things to talk about. I'd love to get some interactivity with you on if you're someone who is a 3D application programmer, if you're someone who implements 3D engines, ray tracer, rasterizers, or if you do both of those things. We'd love to hear about how ANARI can be interesting to you, it's already useful to you, or if there are issues that you see. It's really the dialogue is what I'm interested in. So we'll talk about what's available in the SDK, some new additions that we have, like a Blender add-on, a Hydra delegate for OpenUSD, and then, of course, implementations and applications already seeing success with that. So thanks, that's ANARI.
So we're 45 seconds ahead of schedule, so over to you, Alexey.
Hi, my name is Alexey Medvedev. I'm working for Meta. And, so I'm a chair of 3D Formats Working Group. So we mostly known for glTF standard, and I will cover 3D commerce group as well. glTF itself is not just 3D asset format, so in reality glTF today is an extensive ecosystem that includes a lot of open source tooling for the exporting, optimizations, verifying to just like make sure we're consistent across the software, across the vendors, and basically our goal is to be pervasive as much as possible, and meantime our goal is to be very friendly for actual delivery. So we picture glTF as the last mile file format that we deliver asset in most friendly format for the actual runtime execution, and be friendly for any kind of devices that we can work with. ISO glTF is one of the Khronos ISO formats of standards. So Khronos actually is able to do these publicly available specification submissions. That means we can do our submissions by our pace and keep the industry updated all the time when it's necessary. And yeah, glTF is already ISO standard. We collaborate with our colleagues with OpenUSD. We're not fighting each other, actually, so we found like a great way to collaborate. We develop actual software even to be able to interoperable. And we have presentation, actually, yes, that's tomorrow. Please join us and you can hear more about how we utilize USD and exchange content with glTF. glTF PPR is one of the most rapidly evolving spec. If you don't know, glTF basically consists in several major main pieces, like a core that describes geometry, and the way how glTF describes the materials actually is just like a specification that you use the actual physically based parameters to describe a wide variety of materials. We started as the metallic roughness model a while back, 2017, so almost every year since 2020 we ratify new extensions. In 2020 we ratified clear code, sheen, and transmission. Then this year actually it's why bigger effort because it's way more computationally expensive and way richer materials. We already ratified anisotropy and dispersion, and it's more extensions coming. Actually, we'll cover this during our talks as well. We have an agenda later. Yes, Material X has the glTF. If you are not, actually, that's easy to interchange the data. If you don't use glTF directly, you still can use PBR material if you want to. This already integrated into Blender, by the way. Another effort actually recognized it's a lot of use cases when, especially for e-commerce, etc. They're using glTF, and there's a strong desire to be consistent visually. And we kind of recognize the actual tone mappers that industry get used for movies or games. It doesn't fit actually the requirements for the e-commerce because we want to more or less neutral light environment. And we develop our own neutral tone mapper. That would be a talk during SIGGRAPH when I explain all the technical details. Again, highly recommend to check it out. We implemented glTF here for iOS. Apple by default doesn't support glTF, so their primary format is USDZ. We decided to create our own viewer that you can download. It's open source, it's completely free. You can load any assets, you can even use the AR framework to locate the object in your spatial environment. And let's quickly touch our future roadmap. So our vision is glTF, it's not only 3D assets. In fact, we're moving to the direction glTF is a virtual object for smart objects. And this year we'll most likely ratified several important extensions is interactivity, physics, and complex scene in audio, which allows create way wider experiences based on glTF. Let me really quickly go through them. So glTF interactivity allows us to create behavior graphs and embed them as the actual sort of node-based scripting model into objects. It's super strict and it has all the requirements to be safe and as much as necessary. Draft specification is already on GitHub. Feel free to try and play with it. And on the slide, you see the actual interaction examples that you can create. Again, that's one single glTF asset with extension that enables all the runtime functionality. glTF physics, that's another extension that creates a new set of the capabilities for glTF. Typical glTF, again, we are not dictating any runtime implementation. We provide the necessary information to implement runtime to be consistent. glTF physics working exactly this way. We create two extensions, one for collision shapes, second one for actual rigid bodies that you can describe the properties for the objects. And if you use your physics engine, it's completely agnostic to actual implementation. You can see the objects that will start to interact and use those properties. And this is your code. You can play with it with an example. Another big one, it's external references. We see a lot of strong desire to extend using these assets for the complex scenes, and this is our way to approach. That's a new file extension and slightly new schema that allows us to use glTF files as leaf nodes, and you can generate your scene graph based on this new schema. And final slides about our 3D commerce effort. So our goal is to be pervasive as much as possible. We want to be everywhere. We want to be super friendly for the commerce. For this, we develop a lot of software internally. We have our reference viewer, we have validation tools that you can run and check the schemas or like check the requirements for the assets. We have our own asset library if you want to implement your viewer or check how existing viewer works. You can do this. We are working on the asset generation tool that allows to create the actual assets, and we are working on the render infidelity showcase that basically allows to compare different engines implementations and see if they perform well. And this is in line for our goals. Tomorrow it's 8:30 to 11:30, and Wednesday it's, I think it's from 9, should be after lunch. Yes, it's from 1 p.m. when we will go into all those topics really deep and cover and can answer a lot of questions. Thank you.
And big thanks to Ken. This is like a smoothly oiled machine that comes in at just the right time. Thank you, Ken.
A lot of breath. This convention center is huge. All right, so hi, my name is Ken Russell, Google, and we're going to talk about WebGL and WebGPU. Khronos is very nice to give us some space to talk about WebGPU here. It's a standard developed over the W3C, but as you probably know, Khronos and W3C have had a long-standing relationship bringing awesome, fast standards to the web. GPU accelerator, of course. So here we go. Let's go. Okay, yeah, so again, Khronos is totally supporting development of the WebGPU API at the W3C. We're all working for a smooth transition from the WebGL to the WebGPU API, but we're not trying to Osborne WebGL. Who gets that reference? You really should look it up. The Osborne computer was obsoleted by its owner promising the next awesome one, and everybody stopped buying the current one. The company went out of business, and the next one never came out. WebGPU is already out in Chromium, and it's in Safari Tech Preview and Firefox today, so you don't have anything to worry about there. As soon as it ships on iOS, I think we'll all agree the big cyber leap. So any Apple engineers out there, you know what we're waiting for. Anyway, it brings compute shaders to the web most significantly, but also a lower level stateless API, just like Vulkan, D3, D12, and Metal. Simpler to use than I would venture to say any of them. And we're aiming for as high performance as we can possibly get portably with it. But anyway, WebGL is out there today. It's going to be out there forever, basically. So we continue to evolve it. I'm going to show you some awesome extensions that have been introduced. Please continue to use it, and also look forward to WebGPU. Try it out. Tell us if you run into issues. We've had some really awesome collaborations with companies like Unity, who've been putting the API and shading language through its paces and showing us where there were actually problems with the specification that we put together, and so change it. Okay, I think I just ad-libbed all this, so I didn't even look at this, but it's pretty much the state of things. So one of the awesome extensions that is coming, it's not yet in community approval, is Pixel Open Storage, which Chris Dalton from Rive spearheaded, and Alexey Knyazov, independent of working with Khronos, has made some dramatic improvements to it. Finding all sorts of corner cases in the WebGL2 spec, where if you turn on PLS, you have to disable other parts of the OpenGL API in order for it to actually work correctly. So the spec is being finalized. You can actually try this in Chrome Canary today, even on your mobile phone. Just go to About Flags and turn on the WebGL developer extensions or draft extensions. It's there. This subsumes Blend Equation Advanced. You can implement all of the advanced blend equations in Pixel Open Storage. And there's a demo out there that shows you how to do this. So we don't want to expose the blend equation extension because the drivers implementations are buggy as hell. No offense to any vendors, but they are. So we don't want to expose them. We want to expose this. This is fully general. Lets you basically do programmable blending, and Rive's put it to use in their own renderer, and it's wicked fast on Apple Silicon. And will be on other platforms as well. Anyway, so that's that. There are also a small grab bag of WebGL extensions that Alexey spearheaded. He went through the entire OpenGL ES registry and found all the useful ones. And was like, all right, can we put these 14 extensions in WebGL to, not at this date, not at this point. We're trying to finalize things. It's like, we'll make developers' lives easier. It's like, all right, okay. So we came to consensus among all browser vendors. These are all community approved now. So big hand to Alexey. Thank you for pushing this forward. If you're watching the recording, hi. And thank you. Anyway, this should probably be about it for WebGL2 extensions, but they're all out there in at least 2 implementations. Probably Firefox will pick up most of these at some point. And these will help you with your content. If you're trying to make WebGL to WebGPU code portable, you can use the clip control extension and switch your coordinate system, both for depth and the Y flip, and that all works. So, and there were bugs in that, by the way, so we have to work on this. All right. Now for WebGPU. So the WebGPU ecosystem is really solidifying. It's really cool to see all the awesome stuff that's come out. You may not know this in the graphics community, but this has taken off like a rocket ship in the web AI ecosystem. Within like a month or two of WebGPU's release, there were like Hugging Face models running on the client with no app install, just downloading the model, downloading some compute shaders and running it there, getting really good performance, and we're only making this get better. We're adding more and more extensions to the compute shaders to expose the hardware capabilities. So anyway, you can try it in all the browsers today on various platforms. The spec itself is nearing candidate recommendation. So Firefox is a great steward of web specifications and said, this is not a spec until it's a candidate recommendation, so we're all working toward it. Our colleague Brandon Jones in the back, hi Brandon, has been landing a bunch of pull requests in the specification recently. Our colleague Kai Nanamiya has been reviewing, oh, there's Kai, you can see. So if you want to talk to the spec folks, there they are. We're all here, very approachable, very friendly. Anyway, we're going to transition to a living standard. I don't think this is over-promising anything. I think all the web browser vendors are on board with doing this. It's the way to keep things moving forward gradually. Anyway, some of the really cool stuff is 3JS's WebGPU backend. So if I can talk about this for just a minute. So a couple of really talented developers are out there and have contributed to it for a while. They, just make sure. They had to create a new shading language. No gasps. But they call 3JS shading language. And the reason is that they were trying to make the WebGPU backend really seamless to adopt. So there's a new WebGPU renderer, and it's kind of like a one-line change in your 3JS code. It's like, instead of new WebGL renderer, we say new WebGPU renderer. Sounds simple, right? Well, all the materials are changed because all the materials were written in GLSL before. Obviously, that's not going to work. They tried transpilation of GLSL to WebGPU shading language in JavaScript. They got some shader toys running, but it's not the way to go. So they built a new node material-based system. But the way that that's implemented is on top of a new 3JS shading language, and that itself can spit out both WebGPU shading language and GLSL. So you change your 3JS app, and you say new WebGPU renderer, and that is a WebGL 2 fallback. No gasps of surprise. Some of the compute examples work too, and they're using transform feedback. Now, this is not going to work in the general case, but you'd be amazed at how much of the WebGPU samples are actually working in Firefox and Safari stable today, and they will just auto upgrade to WebGPU and more features and higher performance as those browsers bring WebGPU to their implementation. So anyway, there's a lot of really cool stuff going on. Please try everything out. Tell us how it's going.